In this demo, we're going to see how we can compile ROMs on the cluster. So before we begin, we have to log in on the master node where we're going to compile the code. We do that by typing X and then return. We put our password, and we are now logged into the master node. Let's go into the ROM's source directory, and let's there's a little bit of junk here. So this is the source directory as you will find it. And so as I said, at this point we have configured an application by editing the file cppdefs.h and include. Okay, and we've selected all the types of options that we want to use, define Coriolis and so forth. Okay, so now we need to compile the code. This ROM's code uses the make file to compile, which is basically a file containing a rule of instructions of how to compile the code. This is contained into this make file over here, and this is a particularly long file. All you need to know about this file is that the pound sign represents lines that are comments, and other things that you may want to parameters that you want to toggle in this file are for example this MPI switch, which stands for multi-parallel computing. If you want this to be on, meaning that you want to use multiprocessor computing, then you have it on, or otherwise you just take it out like this. Okay, but I actually want to keep it on. You have different types of multiprocessor type capability and so forth. And the other important thing that you want to keep in mind is that you have different types of compilers on each system. Each Unix systems may have different compilers. For example, Linux, this particular Linux box has two compilers, which is the Intel Fortran compiler, which is the iFort compiler, and the PGI, the Portland Group compiler. So if you want to choose one of the two, you just go down here and you just put in this fort string either iFort, or if you want the Fortran compiler, PG. Okay, these are really the only places where you want to edit. If you go further down, okay, this is the end of the user-defined options. So from there on, all these other things is you want to ignore and you never want to touch. So this is the first part of this file. For the system, it is already configured, so you don't really need to do anything. Keep in mind that if you are in a different system and you switch compilers, in general, you should be just fine by just editing this fort string where you put the type of compiler. If, for example, in your system you enter, say, the iFort compiler, and the compiler fails to compile, okay, so then that's the case when you want to go in this directory called compilers, okay, which contains, if you remember from the README file, the list of templates for how to compile the code using different types of Fortran compiler. And this works like this. So these files begin typically with the name of the operating system or architecture, in this case Linux. Then they have the compiler name, which could be G95, IFC, or iFort. So this is, for example, the one that we're using, and then that's it. So if you open one of these files, you'll typically find all the glory details of how the iFort compiler has all its flags in order to compile. If something goes wrong, it means that some of these flags need to be changed, and this is takes a little bit of experience, and you only do it once when you install the ROM's code on your particular system, and you can ask for some help to some more experienced users of Unix that you typically compile stuff. This is just a one-time thing. Okay, so having said that, let's go back to our directory. So really, after you edit the include file, the cppdefs include, so we've done this one here, so we have that done. Really all you need to do here is you type gmake, okay, since the make file is already pre-configured to use the Portland, I think the Intel Fortran compiler in this case. So if you type gmake, you'll find that this thing starts to compile, and you could see, if I stop this 1 second, the first step of the compilation is it has two steps. The first one is to run the CPP option on the on this whole thing here. You can see it's a very long string, and in this case it's running the CPP option on this Fortran file called mod_forces. You see it here just vaguely, and it redirects the output. And so in fact this Fortran little F90 is the stripped down version of the Fortran source code that retains only the options that you have enabled. So that's very nice to read. If you want to look at it, you see it's very clean Fortran code, and you can scroll down, and this is what this is, and it's much cleaner than, of course, the original one, which was in modules here, this Fortran code, where you see here, if you go forward down, you have a whole bunch of if, def, these are all in directives of the code, so that it retains all these different parts of the code. Now, as I said, gmake is to compile, and you can resume your compilation at any time by just typing that. If you think that in general the compilation is going too slow and you have more CPUs available on this particular node, which you do, you can try and use more CPUs to compile. So first I'm going to remove all this stuff. I'm going to start from scratch by typing gmake clean. I do that, and see it removes all these little .f90 files and so forth. And now I'm going to compile using 4 CPUs instead, and you'll see that the compilation process is much faster. Okay, and I'm going to interrupt now, and I'm going to type gmake clean. Okay, and so I'm back to the original version. Now, one thing to keep in mind, that if you do gmake and you're compiling, and at the end of the compilation, let's actually wait, because it's kind of important to make sure that it works. So it's going through all this. Now it's using this MPI F90, which is the script, and it's done. If I now type in ls -rtla, which lists in reverse chronological order, you find that you have a whole bunch of new files here. You have all these .o files, .mod. These are all the leftovers of the compilation. And at the very end, the last file created is actually the binary file here in green, which is the actual executable. Okay. Now, because we don't care about this other junk, I'm going to type again gclean. Okay. And if I now type L, all that's left is the executable here, which is the actual ROM's binary file. So I'm going to remove that too, because I don't want to keep it now. Now, this is one way to compile the code, but I prefer, I have a more personalized version of doing it, which could be handy for the training, which is inside the directory application. If you type L, you'll find that this directory now has one example here for Coriolis. Okay, has 3 files. The first file here, Coriolis _cppdefs.h, contains my stripped down version of the CPP defs, so it's a copy of that, and so that I have it called Coriolis _ like this, so I can have a whole bunch of these stripped down versions, for different applications if I need to. So this is my code here. I'm gonna close that, and then I have a compiler script which does all the above for me and more. In that, if I open this, this is a shell script, which means that what you find on this file, aside from these statements that that begin with the pound key, that is there are comments, all these are just regular commands, like if in the same way that are executed in the same way as if you were typing them on the console like this. So for example, I can type the command ls, and then I can type the command, for example, pwd, and instead of typing this command on the console, I can put this command in a file and then execute them all at once. And if I do that, that is basically a script, in this case a shell script. So let's look at this shell script, and this shell script is very simple. There's 2 parts. There's the first part that has definitions of variables. It's only 3 variables in this case, and that's the only thing that you want to touch. And then there's a whole other bunch part that is something that does all the compilation process, and it does other things for you. So, but let's look at the variables that you define here. So the first variable is src equals, and so what you do here is you say it's equal to my home directory, which is contained in this dynamic variable. In fact, this is the home variable, and you can recall the value of the home variable by just putting a $sign in front and then enclosing the name of the variable in the 2 graphs. Okay, so this particular variable contains the home directory information / roms src. So now here basically this first variable, I'm assigning a new variable that has the path of my home directory. Following this, I have a new variable, which is the executable. I want to specify where to store the final ROM's executable file, and this is going to be in my home directory here, /roms example /coriolis /bin /coriolis.roms, and this is a directory that I prepared where I'm going to run my Coriolis example. And then you have to tell initialize a variable that contains your stripped down version of the cppdefs files. In this case is this coriolis.h contained in this directory. With this in mind, then I can just go back here and run this script here, which is kind of nice, and I just wait as I did before, and I am sorry for my talks. And anyway, when this is going to be done, which is very soon, in fact right now, you have that the compile is complete. It lists you the location of the binary file that it just created. So you have the date here and the size of the file, and then it says done. So I'm basically done. Now the nice thing of this is that if I want to change my application, for example, suppose that I want to run this Coriolis application with no advection, I can copy this cppdefs files into a new file that I'm going to add the no advection here. And once I copy this, I can edit my new cppdefs h file, and here I want to turn off the advection, so I'm going to do undefined the advection term here. Or alternatively, I can just delete this string, because if something is not defined, it is automatically undefined. So I save this now, and so now I have a new .h file with a new type of application, which is the Coriolis without advection, and I can create a new script, a new compiler script, by just copying that into, say, no advection, like that. And then I can open this, make sure that the first three variables are correct. So here the executable, I don't want it no longer to be Coriolis, but I want to add no advection here. And then I'm going to say that my cppdefs stripped down version is now this particular file here. Now I now have two applications here. I just simply copy this into a new one, and I can run this again, and it will compile, and so forth. I'm not going to wait for it to finish. And so the idea now is that I can retain all these applications, and I have a compile script, so at any given time I can go back and recompile the code without necessarily going in the include directory every time and opening the cppdefs cppdefs.h. Oops, sorry, this is not cd, doesn't open it. So I don't have to every time go here and change this file and then compile and change the file. But like this, I can basically retain a history of all my applications, and I can rerun them anytime I want. So with this, I'm going to stop this particular demo, and of course I'm going to clean again my compilation process, and that's about it for the compiling.